So in question 11, you're given an infinite series, the sum n starting at 2 to infinity, of 1 over n times the square of the natural log of n. And as with just about every series that we'll analyze, the question is simply, does it converge or does it diverge? So, of course, being that this is 10.3, they've actually given you specific directions on how to assess the convergence of this. They've told you, try the integral test. So how does the integral test work? What would you like to do here to get our integral test started? So we've got an integral to do. We know exactly the integrand that we're integrating. Namely, we're going to be integrating what function? Just trade out your n's for the continuous variable x instead. And we'll be integrating that as an improper integral from something to infinity. And exactly what that something is, if we want to be technical about it, is going to depend on whether or not we'd like to show that this integral converges or diverges, so that we can conclude that the series does the same thing. So I'm actually going to be ambiguous about what that lower limit is for the minute, and then we'll sort of go back at the end and figure out exactly what we want there. So the real challenge in this problem, I think, is evaluating this improper integral. We need an antiderivative for 1 over x times the square of the natural log of x. So how are we going to find one? What's our technique here? Yeah?
Should we separate 1 over x from 1 over ln of x squared?
We could do that. So split this fraction into two pieces, like that, and give each one its own numerator. Okay? How does that help? I think it does help, but how?
Ln of x is 1 over x dx.
The derivative of ln of x is 1 over x. Right. So this suggests which integration technique would be useful here. If I have an inside function whose derivative happens to appear on the outside, I'm talking about a u substitution. U equals the natural log of x, so that du is 1 over x times dx. And so that substitution turns this natural log of x here into a u. It turns this entirety of 1 over x and dx, this whole product here, together, makes us a du. And so our integral becomes much easier on the eyes. Namely, it just becomes 1 over u squared du. And what's an antiderivative for 1 over u squared? Negative 1 u to the negative 1, aka negative 1 over u. And because we don't want u's, we want x's, we'll just trade those u's back out for x's. We want to do that anyway before we evaluate the limits of this integral. So let's do that now. Minus 1 over the natural log of x. I'm supposed to evaluate that from some lower limit that I don't know and I might not care about, but definitely the upper limit has to be allowed to tend toward infinity. So using the usual improper integral trope, we're going to let this upper limit be something concrete, and then we're going to let that something go to infinity. Let's choose a lower limit now, just for fun. Let's say the lower limit is, I don't know, 2. Then when I evaluate this at n and I evaluate it at 2, I'm going to get negative 1 over the natural log of n minus negative 1 over the natural log of 2. And the question is still, what happens to that quantity as n tends to infinity? 1 over infinity is what the first term becomes, and 1 over infinity is just a code word for 0. So that term goes away in the limit. And we conclude that this improper integral converges or diverges. This improper integral converges. Its value is finite. And that's good news, because what does that mean about our series? It also converges. Because the series does what the integral does. And if we want to be really specific about why, then what we really wanted to do, let me clear out some room here. What we really ought to do to prove this rigorously is, in order to prove that a series converges, do I want it to be less than the integral, or do I want it to be more than the integral? In order to show that the value of the series is finite. What do we want?
Less.
We want the series to be less than the integral, because there are only two fruitful comparisons in calculus. There's less than finite, which always implies finite, and there's more than infinite, which always implies infinite. These are the two comparisons that you want. And so if we've just taken an integral and we found out that the value of that improper integral is finite, then what we really want is we really want to show that the value of our series is smaller. 1 over n natural log n squared, n running from 2 to infinity. And so really, what would I need my lower limit to be on my integral here? In order to guarantee the integral is bigger than the value of the series. I would really need a 1 here. But there's a hidden problem with putting a 1 at that lower limit. What would have happened down here at the bottom if I had instead had a 1 as the lower limit in my integral? Yeah, that would have been actually another problem. We would have made this integral improper in two different ways if I had a 1 at the bottom. So that when n tended to infinity, this left-hand term would still tend to 0, but this right-hand term is undefined. So technically, the value of this integral from 1 to infinity is not finite. That this integral would still be infinite. So the way we would patch this up is we would do a trick that is incredibly valuable, and that is, remember that convergence of an infinite series is not decided by its lower limit. Convergence of an infinite series is decided on what happens as n tends out to infinity. So that means that all I need to do to show that our series converges is I can show that any series with any lower limit that I want to converges. I can adjust that lower limit if I need to, if it suits my purposes. And here it does suit my purposes. Let's just bump that lower limit up by 1. Let's make it n equals 3 instead. And when I do that, now I can make the conclusion that, well, the series beginning with n equals 3 is less than or equal to the integral whose lower limit is 2. There we go. And because of that, and because we know that the improper integral from 2 to infinity is nice and well behaved, natural log of 2, now this actually has a value, namely 1 over ln 2, then we can guarantee that our series, starting from n equals 3 to infinity, is convergent. Because its value is definitely less than or equal to the value of the integral, which is 1 over ln 2. And because the sum from n equals 3 to infinity converges, what's the only difference between the sum from n equals 3 to infinity and the sum from n equals 2 to infinity? What's the only difference between these two things?
You're just missing a 2 to infinity partial sum.
Yeah, I'm just missing actually only one term from this series. I'm only missing the n equals 2 term. And the n equals 2 term has a finite value, so that's not going to screw up our conclusion. ln n squared plus the term for when n equals 2, which is 1 over 2 times ln 2 squared. A little cluttered, but that will do it. Because what we've done is we've shown that this infinite series with n equals 3 to infinity has a finite value that is less than or equal to 1 over ln2. And because the original series we started with, this one over here, because the original series is just equal to that plus some nice, well-behaved finite number, 1 over 2 ln2 squared, that must mean that our original series converges also. So there's a couple points in here. The first is about the integral test, that the series does whatever the integral does, and the lower limit that you use on your integral is dictated by the lower limit on your series and the conclusion that you're trying to make. Are we trying to show this is convergent, or are we trying to show this is divergent? But the second point is that we can play fast and loose with that lower limit when it suits our purposes. If we end up with an improper integral that doesn't converge, like we did here, we had 1 to infinity and it didn't work, we can shift that lower limit and shift the lower limit on our series, in other words, the first term in our infinite series, and that won't affect whether that series converges or diverges. In fact, we can throw out as many terms of the series as we want to, as long as it's finitely many, and we won't affect whether or not the series converges or diverges, because convergence is decided out at infinity and not at the lower limit of your series.